Okay, so today's topic is a convexity of a function. So let's suppose that we have a function f that takes a real number and gives out a real number. Our question is, what is the condition so that f is convex. For example, a convex function could look like that. So we have a interval like from x equal to a to x equal to b in the real line, and this is fx. We could have the function which looks like this. So this is a convex function. Now we will derive what is the condition that the function f respects. Okay, so let's start with a real line. Okay, and we start with x equal to a to x equal to b, where a and b are any numbers. We want to define a parameter lambda which is in range 0 to 1, and changing lambda will make us traverse through this line. Okay, now how can we construct construct this parameter lambda? So consider a arbitrary point which is x. Okay, so we can now write lambda is the as a fraction of x minus a. This is x minus a over this is b minus a, where we have assumed that b greater than a. Okay, so from this equation we can write x equal to lambda b plus 1 minus lambda a. Okay, let us draw this function again. So we have x equal to a to x equal to b, and we have this function x equal to f of a, and this height is f of b. Okay, so now what could be the convexity condition of a function? Note that if we draw a straight line connecting these 2 points, then all the values of this function between this range a to b must lie below the straight line. So this is a convex, this is a convex, this is also a convex function. Every things are convex here in the below region, but here this is a concave. So this is a concave, and these are the convex function, convex. Okay, so now let us formalize this thing. So let us draw it in a bit clear. Yeah, this is our desired convex function. Let us derive the equation of this straight line. Okay, so let us call this straight line as fs of x. So s for straight line. Now how can we derive this straight line formula? To derive the straight line formula, we take a point x, and this is fs of x. Okay, now we know that the slope of the straight line is constant. Slope calculated between x equal to a and x equal to b is f of a minus f of b by b minus a. This slope should be equal to the slope calculated between x equal to a, this point, and x. From these 2 points we can calculate the slope as f of a minus, sorry, it will be fs of a minus fs of x by x minus a. Now we can write it as x minus a by b minus a equal to fs of a minus fs of x by fs of a minus fs of b. Okay, now note that this term is equal to lambda, so we have lambda equal to fs a minus fs x by fs a minus fs b. So we have fs x lambda fs a minus fs b minus fs a, this is minus, so we have fs x equal to fs a minus lambda fs a plus lambda fs b. We can simplify fs of x equal to fs of a 1 minus lambda plus lambda fs of b. This f of x is always less than fs of x, so we have f of x is always less than or equal to fs of x. Now we substitute the our x from this equation, lambda b plus 1 minus lambda a, this is the x, so f of this thing is less than, we rewrite it as lambda fs of b plus 1 minus lambda fs of a. Now here is the crucial point. Here we see that fs of a and f of a are the same, right, because they meet at the same point. So we have fs of a equal to f of a and fs of b equal to f of b. Therefore we have our desired result. The condition of convexity of a function is written as lambda f of b plus 1 minus lambda f of a is always greater than or equal to f of lambda b plus 1 minus lambda a, where lambda is in the range 0 to 1. So lambda equal to 0 gives x equal to a and lambda equal to 1 gives x equal to b. So thank you so much. See you in the next video.